All right, this video is about the characteristics of polynomial graphs. This year, just because we don't have a whole lot of time, we're not going to be doing any graphing by hand. We're going to look at the important characteristics. So you'll be given all the graphs, and you need to point out the important characteristics. Now, in SM1, you went through graphs that were linear, so they made lines. Okay. In SM2, you went over graphs called parabolas, so they made kind of the skinny U shape. These were of the form ax squared plus bx plus c. Lines are of the form mx plus b, right, your slope, y-intercept. So you've done linear. You've also done quadratic, so 1, 2. This year we're looking at graphs of degree 3 and bigger. So remember, degree is the biggest exponent of your polynomial. Sorry, real quick, forgot to tell you. Okay, I'm using the guided notes. That should be below the resources where you found this video. If you don't have the guided notes, pause the video real quick, get the guided notes. All right. So we're going to talk about degree and how it affects how degree affects the graph and what multiplicity is, and then also the end behavior of the graph. This first part, we're going to talk about the degree and the multiplicity kind of together. So we have some graphs here that I have for you. I'll probably be drawing these up on the board. So the degree of the graph in its most basic form tells us how many times the graph crosses the x-axis. So remember, from SM2, there was something called the fundamental theorem of algebra. That just tells us that the biggest exponent, or the degree of your polynomial, is how many solutions we should have. Well, a solution, or a root, right, that's a synonym, is also a synonym with x-axis or x-intercept. So a root and an x-intercept are synonyms. We say root when it's written down as x equals something. We say x-intercept when it's a point, when it's a location on a graph. So let's look at that first graph. Kind of looks like, this isn't going to be perfect, but you'll get the gist, I believe. Kind of looks like this. All right, so the x-intercepts, how many x-intercepts are there? There's 1 and 2. Okay, so that means it's degree 2. I'm going to put the next one on here too. So here, let's see, we have this one, and it's a little bit longer. It kind of comes down like this. Okay, this one has 1, 2, 3, 4 x-intercepts. So degree 4. So just by looking at the graph, we can tell how big the polynomial was, or the degree of the polynomial. Okay, so this one would have had to have some kind of x squared in it. This one, as the biggest exponent. This one would have had some kind of exponent of 4 as the biggest exponent. We don't know the numbers, we don't know the coefficients, or what else came yet, but we do know what the biggest exponent was. Let's do the next two together. So let's see, this next one kind of looks like, let's see, it kind of comes up, comes down, comes up, comes down, comes up. Sorry, I don't know if any of you heard that ding. I didn't have my phone silenced. There is 1, 2, 3, 4, 5 x-intercepts. So that means this is degree 5. So the biggest exponent of the polynomial was a 5. And the very last one, I'm sure you can all guess. Maybe you saw the pattern. We have 1, there's that one, all the way down here, come back up, all the way down like that. 1, 2, 3, 4, 5, 6 Okay, so 6 x-intercepts, degree 6. So that means the biggest exponent would have been a 6 in that polynomial. Okay? All right. Now, there are exceptions to this rule, where the rule of how many times it crosses is how many, or the biggest degree. There are exceptions. And the exception is imaginary roots. So remember, imaginary number is something that has the number I in it, and I is the square root of -1. So for example, 2i is an imaginary number. If a polynomial has solutions plus or minus 2i, they always come in pairs. They're conjugates. So they'll always come in pairs in the real numbers. If a polynomial has 2 imaginary solutions of plus or minus 2i, they're imaginary. Okay? They show up algebraically, but they don't really show up graphically. I mean, you can kind of tell where they're at, but they don't. There's no x-intercept. Okay? Because they're imaginary, so they don't show up on the real number system. And so because of that, sometimes we have graphs that are bigger degrees, but they only cross a couple times just because they have a bunch of imaginary solutions. So let's go to the second page. Turn over the page. Here are some examples. So let's see. We have this one right here. Now this is x to the 4th minus 2x squared minus 6. And when we draw the graph, that's what it looks like. But hold on, there's only 2 x-intercepts, even though it's to the 4th power. So that means that there are 2 imaginary solutions here. Right? It's to the 4th power. We know we should have 4 roots. But only 2 of them show up on the graph, so that means the other 2 have to be imaginary. So here we have 2 imaginary solutions. Actually, I'll write roots. I'm just so used to writing solutions. It's kind of like my go-to word. It's bad. It's one of my bad habits in math is saying solutions instead of roots. So you'll have to be patient with me. Let's see here. The next one is x to the 3rd minus 10. And it kind of looks like that. Well, it only crosses the x-axis one time, but we should have 3 roots. And it only crossed once. That means the other 2 solutions, or the other 2 roots, must be imaginary. So 2 imaginary roots. Last one here. We have x to the 5th minus 2x to the 3rd plus 3. So it kind of goes like this, comes up, makes like a little weird, and then comes back up. Well, there's 1 x-intercept, but we have a degree 5, the biggest exponent's a 5, so we need 5 roots. 1 shows up on the graph, so 1's a real number, right? It's an x-intercept. That means there's 4 imaginary solutions that aren't accounted for here. So 4 imaginary roots. Okay, and that's how imaginary roots work. Now, it's only imaginary. If you have a root that's like the square root of 3, that's a real number. It's about 1.7, right? It goes on for forever, but it'll still cross the graph because it's real. You can find it. It's only if we have imaginary numbers, anything that has an I in it. Okay? All right. Let's move on a little bit. We'll talk about multiplicity. So I have here x minus 1 times x minus 4 squared times x plus 2 to the 3rd times x plus 3 to the 4th. Okay, now there's 1 plus 2 plus 3 plus 4, so 7, 8, 9, there's 10 x's here. So if I were to multiply this out, I'd have an x to the 10th power. That means there should be 10 roots. Okay. So if we find the roots, just like you did in the last video in the practice problems, you set each factor equal to 0. So x minus 1 equals 0. So x equals 1. X minus 4 equals 0. So x equals 4. X plus 2 equals 0. So x equals negative 2. And then x plus 3 equals 0. So x equals negative 3. Well, hold up. Here we only have 4 roots, but we're supposed to have 10. This is where multiplicity comes into play. Notice that these roots are actually repeated. X minus 4 is repeated twice. So x minus 4 doesn't just show up once, it shows up twice. So we call it multiplicity. I'm just going to abbreviate because I don't want to write super small. Multiplicity 2. It shows up twice. Negative 2. It showed up 3 times. So this is multiplicity 3. 1 only showed up once. So this is multiplicity 1. Now normally, if it's multiplicity 1, we don't write anything. It's kind of a given if it's just there. I'll write it there for now. Excuse me. Just so you can see the pattern. X equals negative 3. Well, we had 4 of them, right? To the 4th power, so it showed up 4 times. So this is multiplicity 4. Now, the importance of multiplicities is it tells us how the graph looks at the x-intercepts. Okay, because at the x-intercept, let's say we have something here. The graph can cross the x-intercept, but it can also bounce and touch, right? So touch the x-intercept and bounce back up. Think of the graph x squared. Well, that graph, the vertex is right there at the origin, and it just goes like this. It doesn't cross anywhere. It touches the x-axis once, but then bounces back up. Okay? So the rule on multiplicity, it's not really a rule. It's been proven to be fact, but we'll just call it a rule for now to help you, I guess, kind of understand it. If the multiplicity is an odd number, so 1 and 3, if the multiplicity is an odd number, the graph crosses the x-axis at this root. If the multiplicity is an even number, so like 4 and 2, it will go down, touch the graph at that root, and then bounce back up. Or if it's coming from the bottom, it'll bounce back down. So, for example, this right here, this is a Desmos. I graphed what we just this polynomial right here. I graphed it on Desmos. This isn't exactly what it looks like, right? This keeps going down super far, and this goes up super far. But we're only looking at the x-intercepts. So let me draw it up here on the board for you. Let's see here. So we got this. It's kind of coming down. This is negative 3. It comes up, goes back down, comes down, and then it comes back up here, goes up, comes back down. Now, this looks a little weird on the computer because I couldn't zoom in super far, but what happens is this touches and it kind of goes back up. That's why it looks like it stops, is because it actually goes back up. Okay, so this is negative 3, this is negative 2, this is 1, and this is 4. So notice at negative 3, the graph comes down, touches, and then bounces back up. because the multiplicity is an even number, it's 4. At -2, the graph crosses, right? It goes from positive to negative because it's an even or an odd multiplicity, multiplicity 3. Over here at 1, it crosses because x equals 1 was multiplicity 1, an odd number. And then down here, you see it doesn't cross, right? It comes down and then bounces back up. It doesn't cross the x-axis. It touches x equals 4, this root right here, and then bounces back up because it's multiplicity 2, an even number. So that's how multiplicity works. Some of you might be wondering to yourself right now, are we going to do practice? Yes, it's just hard. It's extremely difficult to do practice on paper like this with graphing. You kind of need something to graph. So in the practice problems, in the modules, right below the guided notes for this video, there are practice problems, and it gives you 3 links to go look at for Desmos activities. So make sure you do those to get your practice in. Let's go to the next page. We're going to talk about end behavior. So end behavior of a graph, essentially, if I have a graph here and it kind of goes like this, essentially what end behavior is asking is at the ends of the graph, so as it's going on for forever, what's it kind of look like? Okay, as this is going on for forever, what's it look like? And we can determine that just by the degree and the sign of the leading coefficient. Here's a little chart for you. It's up here. I'll draw it up here for you. So we have, let's see here. So up here we'll have the degree. Over here we'll have the sign of the leading coefficient. So a degree is a number. It can be even or odd. The sign can be positive or negative. So if it's an even degree, so if the biggest exponent's an even number and the leading coefficient's a positive number, the ends of the graph both go up. I don't care what happens here in the middle. I don't care how many turns it happens in the middle. The ends will both go up. If it's a positive leading coefficient, but the biggest exponent is odd, the ends go in opposite directions. Okay, but as you read from left to right, it's going in a positive trend. So the left tail is down, right tail is up. As you look at it from left to right, it looks like it's going positive because it's a positive leading coefficient. Even degree, negative leading coefficient, they both point down. And then negative leading coefficient, odd degree, it's just the opposite of this. The left tail is up, right tail goes down. Okay, and as you read left to right, it looks like it's kind of going down. All right, so that's the end behavior of your polynomial graphs, depending on the degree and the sign. Okay. So looking at this, right, if you had something that was negative 3x plus 2x squared plus 5, okay, the biggest exponent is a 2. It's a positive leading coefficient, so both of them will go up, both ends. I'm gonna leave this to you to look at. Okay, if you need extra stuff to look at. What I'm going to talk about is how we write end behavior. There's a notation that we use. So when the degree is even and it's a positive leading coefficient, what we say is as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to positive infinity. I'll show you this right now. So let's say we have a graph and it looks like this. Okay, so both the tails are going up. That means that it's an even degree, positive leading coefficient. Now, if you look, as x goes to infinity, so our x-axis, as it's going that way, which way is the tail going? Well, the tail's going up, right? So, as x goes to infinity, y goes to infinity. As x goes to negative infinity, so as we go this way, negative, which way is the tail going? Well, it's going up, so y is going to infinity. Okay, that's the notation we use. Let's do another one. Let's do this graph. All right, so this one it's an odd degree, positive leading coefficient. So as x goes to infinity, as x is going that way, x goes that way, y goes up. So y goes to positive infinity. As x goes negative, so as x is traveling this way, negative infinity, which way is the tail going? Going down. So y goes to negative infinity. All right. Sorry, I thought I didn't start the video there for a second. I've been going for 20 minutes and I almost freaked out. All right, let's do this one. So this one, the degree is even. The sign is negative of the leading coefficient. So as x goes to infinity, positive infinity, as x is going to the right, the tail is going down. So y goes to negative infinity. As x goes to negative infinity this way, which way is the tail going? Down. So y is going to negative infinity. And this kind of makes sense, I hope. See how y is the same? It's because the tails are going the same direction based off of our chart. Okay, next one. Let's do like that. So this one is odd degree, negative leading coefficient. As x goes to infinity, so as x is going that way, which way is the tail going? Down. So y goes to negative infinity. As x goes to negative infinity, so this way, y goes to positive infinity. Right, goes up. And this one makes sense, because odd degree means that the tail should be going different directions. So one goes negative, one goes positive. So it makes sense. All right. If I'm not mistaken, I think that's it for this lesson. Yes. So once again, the practice for this stuff is in the modules. So go in the practice problems. There's 3 links. Do all 3 of them. It talks about degree, multiplicity, and behavior. So go ahead and go into those practice problems for you to do some practice. Click on the links, and it'll allow you to go to the Desmos activity. All right. Once again, if you have any questions, you need any extra help, I'm always available to you. Just come in after school, make a Zoom appointment, something like that. Please don't let any kind of misconceptions get spun out of control to where you're playing catch up in a month. Be proactive. It's easier to get things done now rather than later. Have to do it a second time. But just remember, I'm always there for you, and let me know if you need anything.